All right, this is the second lesson of the week, April 20 through 24th. This is a special section. This is not in your book, but it's something that I think chemistry students ought to see, so I'm going to take you through it. If you need more resources, I can get those to you, but I think you'll understand it from this section. One of the things that we haven't talked about much is that we talked about it back in gases with the gas laws. The gases are affected by both temperature and pressure, but actually that is true with solids and liquids as well. We talked last video about vapor pressure, that vapor pressure builds up to a certain point where we hit an equilibrium where basically every water molecule that leaves, another one comes back in. It turns out that atmospheric pressure helps to change both melting points and boiling points, and also a place called the sublimation point. In other words, whether something is a solid, liquid, or a gas for that particular substance depends upon both the pressure and the temperature. Now, some of you may be aware of this. Probably the place you would see it the most is if you took a pressure cooker at home. You can take and put water in a pressure cooker. And pressure cooker, you screw the top down or tighten the top down so that the pressure can go way up. There's usually a release valve somewhere. And as the pressure goes up inside, the boiling point of the water comes up. So you can have superheated water that is well above 100 degrees Celsius. You might have discovered this perhaps if you've ever gone camping in the Sierras. When you go up into the Sierras, let's say you're going to make spaghetti and you're going to boil spaghetti noodles in a pot, you will find that they will actually say, because they know a lot of people will take along those type of meals to go camping, it'll say if you're at 5,000 feet elevation, you need to boil the noodles longer. Well, why would that be? Well, because if you lower the pressure, you lower the boiling point. Water in Denver, Colorado boils at maybe 80 degrees Celsius. I'm just guessing, but it's below 100 degrees. That's because there's less vapor pressure at that temperature, and it requires less temperature for the molecules to escape. Just so you know, boiling, what we call the boiling point, is when vapor can form inside of the liquid. And that means that the air pressure and the vapor pressure are the same. We're not going to spend a lot of time with that idea, but it's kind of interesting. If you lower the vapor pressure, in fact, let me just put that down, liquids boil when the vapor pressure of that liquid is equal to the atmospheric pressure. So if you lower the atmospheric pressure, you will lower the vapor pressure, and that means boiling will occur at a lower temperature. Now, what I want to show you today is something called a phase diagram, which helps to put that all into perspective. And at the same time, at the end of it, there will be a worksheet that you'll be asked to do, and it'd be good to just watch this video again as you were working through it. This weird diagram over here is called a phase diagram. We have pressure in kilopascals, but it could be any value of pressure, temperature, in this case in degrees Celsius. And we have three lines and where they come together. This region of the graph in here is when the substance is a solid. This is when pressures are low and temperatures, when temperatures are low primarily. This region is when it is a liquid. Temperatures are higher and pressures are up a little bit. And then all of this in here is a vapor. Now, not everyone looks like this. Sometimes this will be almost down here at zero pressure. Sometimes this is much lower. Sometimes this curve goes this way. But that is called a phase diagram. And it's called a phase diagram because we have the three phases. This line right here represents the phase change. So this, if we're moving from solid to liquid, this is melting. If we're going the other direction, that's freezing. If we're going this way, this line means boiling. If we're coming this direction, this line is condensing. And by that I mean anytime we touch that line, it's like those plateaus in that other diagram that we had. And then this line right here, if we're going this direction, and I'm actually going to kind of goes more like this. If we go this way, this is called sublimation. And if we go the opposite direction, that's called deposition. I know it's a little hard to read. Sublimation, deposition, melting, freezing, boiling, and condensing. I'm going to take those off of there for right now. This graph does a number of things. If I give you a temperature and a pressure, you can tell me what the substance is at that point. So for instance, if I said that I have a temperature of negative 40 degrees, but my pressure is 75 millibars, not millibars, kilopascals. Negative 40 is here, 75 is here. We would say that this is a solid at that temperature. If I was to say that it was 120 degrees, but 25 kilopascals, well, 120 degrees would be here, but 25 kilopascals, this would be a vapor right here. Okay. If I was to ask, where is the boiling point? Or let's say, where's the melting point? If the pressure is 150 kilopascals. Well, what you're going to do is come up here, let me move that out, to 150, and you're going to go down to here. And this would be boiling at just a little bit below zero, let's say negative 5 degrees Celsius. If I was to ask what is the boiling point, at, let's say 75 kilopascals, then we would come across here, 75 kilopascals, all the way over to here and down. It looks like it's very close to 160 degrees Celsius. Okay, and we could do the same thing with sublimation. Where does it sublime at 25 kilopascals? That would be right over in here somewhere. All right. So that's how a phase diagram works. A little different than that other diagram, but what it does is it allows us to look at something and know what phase or what phase change we're expecting. Now, there are a couple of interesting points on a phase diagram, and I want to show those to you. The first one is called the triple point. And the triple point, by the way, is a point, and a point means you have to have 2 units for it. This right here is the triple point. It's called the triple point because at that point, the substance is melting, boiling, and subliming all at the same time, which means it is both a solid, liquid, all solid, liquid, and gas at that point. If you were in class, I can show you a triple point. It's actually fairly difficult to do. But just to give you a kind of a weird visual, if I had water at the triple point, and there is a triple point for water, and I saw this in college, you can have water which is boiling with ice cubes in it and not changing. The ice cubes aren't boiling away. We are at the right temperature and pressure to cause it both to boil and to sublime and to freeze all at the same time. That's called the triple point. So the triple point by definition is the temperature and pressure where all three phases are present. And in our case, this would be at 40 degrees Celsius, and it looks like about 60 kilopascals. By the way, and because the x-axis is Celsius, we'd say 40 degrees Celsius looks like about 60, maybe a little higher, maybe 62 kilopascals. By the way, this is approximate. And you're going to have a handout where you're going to do that. You're going to look and have to approximate a little bit. So that's called triple point. Other important points on this graph are called normal boiling point and normal melting point. Here's what we mean by that. Melting point and boiling point, you should know what that means. What in the world is the normal melting and boiling point? And what this is, normal means at 101.3 kilopascals. In other words, at standard atmospheric pressure. What we would say is in STP, standard pressure 101.3 kilopascals. Now, you're going to have a graph like this. 101.3 would be so close to 100 that we can approximate it using the 100. But what you would do, let me take that off, is you would get a ruler out and you would draw this along. And where it hits here, we're going from solid to liquid. This is the melting point. And where it hits here, that's the boiling point. So the normal melting point on this graph looks to me like it's at about maybe a little bit past negative 20, maybe, or not negative, a little bit past 20 would be right here, about 18 degrees Celsius. And the normal boiling point would be over here at, looks like maybe 185 degrees Celsius. So that's normal melting point, normal boiling point. There's also something called a critical pressure and a critical temperature. Critical means that something is going to happen or has to happen at that point. Critical means you're right on the verge of something, something's about to happen. What a critical pressure and temperature are is this. It is the pressure above which no more pressure will liquefy the gas. And the same thing with temperature. Basically, above this pressure, you cannot liquefy the vapor. And critical temperature is above this temperature. You cannot liquefy the vapor. Right? These graphs will have a point up here. It's usually not with a dot at it, but that point right here, just like this is the triple point, this is the critical point. And basically what you do is come down like this and across over here. And what we would say is the critical pressure on this is, looks like it's about 150 degrees. 150 degrees, up 150 kilopascals. And this over here looks like it's at about 240 degrees Celsius. Those are approximate. That would be the critical pressure. Once I reach this pressure, even if I put more pressure on it, the vapor's not going to go, it's not going to turn into a vapor. And if I raise the temperature any more than this, all I have is a vapor from here on out. So really what's happening is there's a line that's going like this, and everything over here is vapor as well. Liquid ends right there. That's called the critical point, critical temperature, critical pressure. And then one last thing I'm going to ask you to do in the homework is we're going to talk about what changes takes place, what physical changes take place as we change the temperature or the pressure. So for instance, let's say that we were to take and say that we were at 20 degrees Celsius. Let's make this 10 degrees Celsius. And the question will be asked something like this. If the temperature is held constant, at 10 degrees Celsius, and the pressure drops from, let's say 150 degrees Celsius to 150 kilopascals to 0 kilopascals, what changes, what physical changes take place? All right. Well, here's what's going to happen. And I'm going to try something. I have tried to stay away from the different colored pens, but let me use a green pen here. We'll see if it shows up. Basically, what I'm telling you to do is start right about here and then draw a line straight down to here. All right. I don't know if you can see that well. That's not great, but that's okay. All right, well, what is it right here? Well, right here, for this region, this is a liquid. It's a liquid. Right here, it goes from liquid to solid. It freezes. From here to here, it is a solid. And then at this point, it condenses. It sublimes, and it becomes a vapor at this point. So if the temperature is at 10 degrees, but we drop from 150 to 0 kilopascals, what we would say, our answer would be this. The substance is a liquid. It freezes and becomes a solid. And then it sublimes and becomes a gas. A gas or a vapor. Okay? Now, we could have gone the other direction, and I'm not going to go through this one quite as extensively, but let's say, I won't use green, that doesn't work well. Let's say we did the opposite, that we held it at 125 kilopascals. And I said, you're going to raise the temperature from negative 80 all the way over to 240. Well, then in that case, we would start at negative 80 and 125 as a solid. Here we would melt and become a liquid. Then we would boil and become a gas. And so you would write this one out and just trace it across. Do that line, 125 kilopascals. What happens? Solid to liquid to gas, which is what we typically expect to happen. So there is a worksheet called something like Chemistry Phase Diagram Problems. And that will be, of course, in your folder for this week. But that is a phase diagrams. You will not find this in your book. I don't know why, but I think it's important to be able to see that there is a connection between temperature, pressure, and then the different phases and phase changes that take place.